Hello once again, and welcome to this presentation on flipping the coin paradox. Today we're going to show you how the predictive distribution is used and computed for the coin flip.
I wonder what happens if I flip this coin.
First, let us revisit the maximum likelihood estimate. The maximum likelihood estimate, similar to the arithmetic mean, estimates the most likely explanation for a given observation. It estimates the parameters of a probability distribution by maximizing the likelihood function. MLE chooses the most likely model and ignores all others. Another concept worthy of revisiting to understand predictive distributions is the Bayes theorem. This theorem is made up of four components. The first is the likelihood function, which is the probability of the data given a set of parameters of a model. This is then multiplied with the prior, which is the prior belief of the parameter distribution, and it is then divided by the normalization term, aka the prior predictive probability of D. When we calculate this, we compute the posterior distribution, which entails the probability of a model with a set of parameters given that data. So the posterior distribution is a mix of likelihood function and priors. Let us consider an experiment where we flip a coin. We flip it 10 times, and by chance, we get 10 tails. Now, we ask ourselves, what is the probability of getting tail when flipping the coin again? Now, according to the maximum likelihood approach, we would say that the probability of getting tails for this next flip would be the number of observations, which is 10, divided by the number of trials, which is also 10. This would amount to 1. So we would say for the next flip, we have a 100% chance of getting tails, according to this maximum likelihood approach. And I don't know about you, but when flipping a coin, to me, it makes no sense that we get tails 100% of the time. As you may have noticed, the calculations done here are similar to the ones done when computing the arithmetic mean. So the problem we have in the maximum likelihood approach is that we solely use the data we have. As you saw before, we only had data that supported the tails outcome. Therefore, we concluded that the likelihood of getting tails is 1. Instead of doing this, we should use a prior, which entails a certain belief of a parameter distribution. By choosing a flat prior instead of a prior that has a slope, we make the lack of information explicit. So all parameters are equally likely, and it indicates that we do not know anything about the model before data sampling. So the idea would be to use what's called sequential estimates. Here we want to use the data from previous trials for our model, and we assume a flat beta prior from U. Alpha is 1 and beta is 1. The posterior distribution of that beta prior will also be a beta distribution. Because of this fact, we can use that beta distribution, so the posterior of trial n, as the prior for the next one, so for trial n plus 1. So here you see the process of computing the sequential estimate. With the help of the likelihood function and the beta prior, we compute the beta distribution in trial 1. Then we take this beta distribution and use it as a prior, right here. With that, we calculate the next beta distribution. Then, for trial 3, we use that beta distribution and use it as a prior right here. And we do this n times, n being the number of trials. As the name suggests, the maximum likelihood approach only reports on the most likely model. That's why it would predict that when the data only supports tails, the probability of a tails in the next trial to be 100%. As an alternative to this, we could instead consider all possible models and compute a weighted average of their predictions based on the probability of the model. And this is what the predictive distribution does. It more accurately predicts the probability of the outcome of a trial given the model. This is what the equation looks like. So we integrate over the probability of data given the parameters, which is the likelihood, multiplied by the prior or posterior, which is the probability of the parameters. So before the trial, we look at three main components: The first one is the beta distributed prior or posterior from the trial before with the appropriate parameters. This is what the equation looks like for this component. Then second, we have the likelihood of the possible outcomes, 0 and 1 for the coin flip. So the probability of the outcome being 0, let's say tails, given mu, would then just be this equation, because mu drops out. The probability of x being 1 would have this portion drop out, because when we plug in 1 here, this portion has the exponent of 0. So mu would remain. Now what the predictive distribution does is integrate over the likelihood multiplied by the beta distributed prior, as shown here with the two colors. For further understanding, here you see the prior, the predictive distribution, the likelihood function, and the posterior. So as we said, the prior is flat at the beginning. The posterior distribution for a coin has both outcomes at the likelihood of 50%. Because as we said earlier, the predictive distribution computes the weighted difference. Now for this trial, since we observed x equals 1, let's say 1 resembles heads, this is what the likelihood function looks like. The slope is characterized by mu. The rest drops out. The likelihood of the outcome being 1 is 100% right now. Because the prior is flat, the posterior distribution looks exactly like the likelihood function. Now, before trial 2, we use the posterior distribution as a prior. The predictive distribution, as you see, looks a bit different now. There was an information gain which led to the shift towards the likelihood of 1 being higher. The predictive distribution makes an average of all possible models that are still compatible with the observations. That average is then weighted with the probability of the model. So the alternative hypothesis x0 is not completely eliminated if the trial number is still low, which it is right now, as you see. Unlike for the maximum likelihood approach, a certain, a bit lower, but still prevalent likelihood remains for this case. The maximum likelihood approach would have predicted the probability of x being 1 now at 100%, because it only looks at the point estimate of the most likely distribution. Now when we observe x equals 1 again, the likelihood doesn't change. So now when multiplying the prior with the likelihood function to compute the posterior distribution, we get a slightly more curved function. Since we've observed x equals 1 2 times, the likelihood that x equals 1 is 0 or almost near to 0 is way lower. This is why we can say that all in all, for smaller probabilities of x equals 1, the values are lower. Now you see the previous posterior distribution being used as a prior for the next trial. Due to the fact that the number of observations has increased, the predictive distribution can now make a more decisive prediction and conveys a bigger difference between the probability of event 1 being the case and the probability of event 0 being the case. Now when we look at the likelihood function, we observe a negative slope. This is because the mu of the equation of the likelihood function drops out, and the 1 minus mu is left because in the third trial we observe that x equals 0 and not 1. When computing the posterior distribution now, with the help of the prior and the likelihood function, we see that because we now have observed the alternative hypothesis, that is, that x is 0, the function takes shape. It has a clear peak now. The graph encodes the information that we can exclude the fact that we see only ones due to the fact that we have just seen x equals 0, and it excludes the fact that we will only see zeros. This illustration gives you a sense of the possible evolution of all these components. As you can see from the evolution of the posterior distribution, the model more certainly displays the most probable value mu with an increasing amount of trials. There is more data to evaluate. That is why the function becomes more narrow. Obviously, the same goes for the priors because the priors stem from the posterior distribution of the previous trial. The predictive distribution shows quite nicely how, with an increasing amount of trials, the certainty that x equals 1 is higher is more pronounced. To summarize what we've learned, we can say that the maximum likelihood approach uses only the data. For this approach, we can add information by including a prior, which is a belief on the parameter distribution. The maximum likelihood approach only reports the most likely model. To more adequately predict scenarios that involve a coin, for instance, we can compute the weighted average of all possible models with the predictive distribution. And that's all, folks. Thank you for your attention.